This is the last section in Chapter 3 about the periodic table. Chapter 6, Section 3 is called Periodic Trends. This is going to be the new information for you. The objectives for this section: compare period and group trends of several properties, relate period and group trends in atomic radii and electron configuration. Okay, our review vocabulary. We have a principal energy level, the main energy level of an atom. New vocabulary. Ion, that's really not new, but we'll review that. Ionization energy, octet rule, and electronegativity. Main idea in this last section. Trends among elements in the periodic table include their size and their ability to lose or attract electrons. That's going to be very important when it comes to the chemical reactions, because remember, it is the valence electrons that we're working with that are involved in those chemical reactions. Okay, remember, we are going to start out by looking at atomic radius. The atomic radius, or the atomic size, is a periodic trend influenced by electron configuration. Okay, it is defined by how close an atom lies to its neighbor. Okay, so let's look at the next slide here. For elements that occur as molecules, the atomic radius is half the distance between the nuclei of identical atoms. So ones that are lying next to or adjacent to. So here would be the nucleus and the nucleus. If you measured that and took half, that would be your atomic radius. So these are metallic atoms, and you can see that when you have non-metallic, they kind of squish together, so they're going to be just a little closer. Remember, it is half the distance. Okay, so trends within a period. So remember, we're going across a row, the period. It is going to decrease, the atomic radii will decrease as you move from left to right across the periodic table. So as you're reading from left to right, it's going to decrease. This is caused by the increasing positive charge in the nucleus and the fact that the principal energy level is staying the same. Okay, the valence electrons are not shielded from an increased nuclear charge because no additional electrons come in between the nucleus and the valence electrons, because you're staying within the same energy level, the same orbital. Okay, so as you move from left to right across the period, it's going to decrease. The atomic radii will decrease. Okay, so let's look at that in a chart form. So you can see as you move from left to right, it decreases. Now within a group, so as we go down a group, your radii is going to increase. The nuclear charge increases, and the electrons are added to the orbital in successively higher principal energy levels. So remember, we're adding an energy level as we go from 2 to 3 to 4 to 5 to 6. You're adding a ring, you're adding an energy level. This increased nuclear charge does not pull the outermost electron toward the nucleus to make it smaller, so it's allowing it to become bigger and bigger and bigger. Movement down a group, the outermost orbital increases in size along with the increasing principal energy level, and thus the atom becomes bigger. Okay, I am going to get out of here, and we are going to watch a short video here, and you can get this. This is from Glencoe.com.
Many elemental physical properties vary based on position in the periodic table. We have used relative heights to visualize how atomic radius varies across the periodic table. As we move across any row from left to right, electrons are added to the atoms to counterbalance the increasing positive charge. The electrons are added into orbitals of roughly the same distance from the nucleus, but because of the increasingly positive charge of the nucleus, the electrons are pulled closer, causing the atomic radius to decrease. Moving down any column corresponds to an increase in principal quantum number, which directly relates to a larger orbital, and thus larger atomic radius.
All right, back to the PowerPoint. There we go. So you can see the atomic radius generally increases as you move left or as you move down, decreases as you move left to right. Okay, ionic radius. An ion is an atom or bonded group of atoms with a positive or negative charge. When an atom loses an electron, it forms a positively charged ion. And they always become smaller for two reasons. The loss of valence electrons can leave an empty outer orbital, resulting in a smaller nucleus. The electrostatic repulsion decreases, allowing the electrons to be pulled closer to the radius, closer to the nucleus. So let's look at when an atom gains an electron, they can become larger because the addition of the electron increases that electrostatic repulsion. So here we're going to look at the periodic table. The ionic radii of positive ions generally decreases from left to right. Positive ions. So positive ions is going to decrease from left to right. The ionic radii of negative ions is generally going to decrease from left to right, beginning with group 15. Now remember, these are general trends. There are going to be some exceptions in there too. So within a group, as you move down, they're generally going to increase. So decrease from left to right, and increase as you move down a group. Okay, both positive and negative ions increase in size as you move down a group, and you can see that from this chart here. Okay, the next one we're going to talk about is called ionization energy. Ionization energy is defined as the energy required to remove an electron from a gaseous atom. So you're trying to overcome the attraction between the positive charge of the nucleus and the negative charge of the electron. Okay, so atoms with large ionization energy values are less likely to form positive ions. So we can look at lithium, which has a low ionization energy. Its ability to lose electrons quickly is actually a benefit for us because we use that in our computer batteries to help keep our computers running longer. So the energy required to remove the first electron is called the first ionization energy. And you can see the trends here on this chart. Okay, removing the second electron requires a little bit more energy and is called the second ionization energy. Each successive ionization requires more energy but it's not a steady increase. So if you want to remove the third electron, it's going to require more energy. The fourth electron is going to require more energy. And you can see they have, for a handful of elements, they have the ionization energies written out here. So if we look at lithium, the one we were talking about with the battery, to remove that first electron, it doesn't take a lot of energy, but you can see how far you have to jump up with the energy levels to remove that second electron. You can see they're not in a consistent pattern. As you go up, it requires more and more and more energy. And of course, when you get to down here to neon, remember, it has 8 valence electrons, which means it's very happy. It requires a ton of energy to take electrons from a noble gas, just a ton. And so the elements are like, I'm not going to work that hard. I'm just not going to work that hard. Okay, ionization energy, the ionization at which the large increase in energy occurs is related to the number of valence electrons available. Remember, valence electrons, keep thinking to yourself, the ones in the outer shell. The first ionization energy increases from left to right across the period. Okay, so across the row, across the period, increases from left to right. First ionization energy decreases as you go down the group. And this is because the atomic size increases and less energy is required to move an electron when it's far away from the nucleus. Remember, it wants to be close to the nucleus, but if it gets pushed out, it's going to leave easier. So ionization energies increase from left to right across the period and decrease as they go down. Okay, the octet rule states that atoms tend to gain or lose electrons in order to acquire a full set of 8 valence electrons. Remember, they want to be the cool kids. They want to be the noble gases. The octet rule is useful for predicting what type of ions an element will likely form. The electronegativity of an element indicates its relative ability to attract electrons in a chemical bond. Remember, that's the whole purpose for doing all this, is we are learning what bonds, what chemical reactions are going to occur among these elements as they gain or lose to make 8 electrons to be a noble gas. Electronegativity decreases down a group and increases from left to right across the period. So let's look at a chart here. Okay, once again, I am going to take us out of here and we are going to go watch a short video here. I can get to it.
Electronegativity is the ability of an atom to attract towards itself the electrons of a chemical bond. This property, indicated by the relative height of the elements, is directly related to the electron affinity and ionization energy of an element. In general, electronegativity increases from left to right across the periodic table, consistent with the decreasing metallic character of the element. Within each group, electronegativity decreases with increasing atomic number. The most electronegative elements, the halogens, oxygen, nitrogen, and sulfur, are therefore found in the upper right-hand corner of the periodic table.
Okay, let's go back to our PowerPoint here and take your quiz. Okay, remember, ionization energy is the energy required to remove an electron from a gaseous atom. We are removing those electrons. The electronegativity is the ability of the atom to attract electrons in a chemical bond. So there is a difference. Try and keep those two straight. Oh, shoot. The lowest ionization energy is the first Next question. The ionic radius of a negative ion becomes larger when moving up a group, moving right to left across a period, moving down a group, the ions lose electrons. The answer is down a group. Very good.